Thank you very much for the invitation, first of all. So at the highest level, this is a talk about program equivalence, which is something I'm sure you all know about. It's a major topic of research in programming language theory, and it is something that is interesting from a theoretical perspective, as greatly emphasized, for instance, is an old paper by John McCarthy, but also something that is practically interesting, or interesting from a practical perspective. And that is because this is at the very foundations of program optimization and program transformations. So for instance, here at the bottom of the slide, I have a kind of running example, which is a well-known program transformation, which just expresses the commutativity of sequencing. So we have a nested sequencing, and we want to commute somehow the order in which sequencing is performed. And of course, here there are some side conditions on the free variables in E1 and E2 that I haven't written down. And the way in which you prove that you can perform this kind of program transformation or optimization by means of program equivalence. And in fact, program equivalence has been deeply investigated for pure higher order sequential languages. And in this talk, I will just refer to higher order sequential languages or functional languages, if you like. And as I was saying, program equivalence has been deeply investigated for pure languages. And that since the 70s, I would say, having a look at this list of well-known equivalencies, such as contextual equivalence or logical relations and applicative bisimulations. However, useful languages, as you know, are deeply effectful. So we have languages that combine higher order features with randomness and non-determinism, or with imperative features, and most importantly, with the combinations thereof. So here at the bottom of the slides, there is a very easy program, almost a trivial one, in which we have higher order features via a map function and lambda abstractions, together with several kind of effects. We have randomness, we have rising exceptions, and we have output primitives. So this is a very simple example of a program which exhibit several kind of effects and higher order feature at the same time. And of course, what we want to do is to study program equivalence for this kind of languages, right? So to be able to have a solid foundations for, let's say, program optimization for this kind of languages. And without much of a surprise, what we see is that studying program equivalence for effectful languages is harder than studying it for pure languages. So for instance, we have that for some family of effects, that commutativity of sequencing does hold. This is the case, for instance, for probabilistic languages, whereas for other effects, it doesn't. So for instance, if we have a language with I/O, with input and output primitives, of course, the order in which we execute programs, let's say, inside the sequencing matters. And in those cases, commutativity of sequencing is not sound. It's not a correct transformation. And so far, I mean, in these just toy examples, we have seen how the way in which we evaluate code, or better, how code evaluation influences program equivalences. So the kind of effects that we have when we evaluate code changes the kind of equivalences that we have in programs. But there are also other aspects that modify the program equivalences, the sound program equivalence that we have. And in particular, the one concerning program manipulation, such as whether we are allowed to duplicate code or to erase code or similar kind of things. And here there is a nice example from a paper by Dang and Zhang, in which they start from the observation, the well-known observation somehow, that lambda abstraction in general does not distribute over non-deterministic choices, both pure non-deterministic choice and probabilistic choice. And to see why this is the case, they consider this simple context in which what we have is that we pick the program, we evaluate it, and then we copy the results and we evaluate twice, and then we perform some Boolean test. And the reason why this context distinguish these programs in that in one case we have to resolve the non-deterministic choice twice, whereas in the other case we just resolve it once, right? And the key point is that what we need to do, the kind of manipulation we need in order to distinguish these two programs is to be able to copy the program themselves. And in fact, Deng and Zhang showed that if we are allowed to manipulate programs only linearly, which means that we must use a program just once, then lambda abstraction indeed distributes over probabilistic, over non-deterministic choice. So this kind of manipulation actually influences the kind of program equivalence that we have. And another kind of example, and the same line, comes from confidentiality constraints, which have been deeply investigated in the last decades, in which we may have, for instance, programs that manipulate integers, which are either low-level integers, which means that are low-level security integers somehow, and high-level security integers. And program equivalence for these kind of languages has been used to model non-interference, which essentially means that low results do not depend on high values. So the kind of abstraction that researchers have introduced to understand this kind of code manipulations are known as coeffects, and these are just ways to describe resource and data flow properties of programs. And well-known examples of coeffects are linearity, sensitivity as defined in differential privacy, but also information flow and data confidentiality. Okay, so now that we have some, let's say, informal motivation for study program equivalence in different settings, let me outline the content of this talk. So in this talk, I will talk about coinductive equivalences for higher order languages with effects and coeffects. And with coinductive equivalence, I actually means a single family of equivalences, namely applicative bisimulation, which is probably the most well-known coinductive equivalence for higher order languages. And with coeffects and coeffects, what I mean, well, I will tell you during this talk what I mean with coeffects and coeffects. But for now, let me just tell you that I will show you languages in which we have two kind of modal types. One for giving information on the effects that can be produced during the computation, so on what happens when we evaluate code. And another modality, a box modality, which expresses the kind of capability of code, namely the kind of manipulation that we can make on code. And the kind of results I will show you are essentially compositionality theorems, which just states that the equivalences studied are congruences, this way enabling compositional reasoning about programs. Okay, so let us begin with effects, which are definitely much better understood than coeffects. And let me begin by fixing a vehicle language for this talk. I would consider a fine-grained call-by-value lambda calculus, which means that we have a syntactic distinction between values and computation. And the value is the result of a computation, so it's something that should not be computed somehow. So for instance, the numeral 2 is a value, whereas a computation is a program that should be computed, and they produce values, and they also may produce effects, right? And we also reflect the distinction between values and computation at the type level, whereby computations have monadic types in the spirit of Moji, which I wrote using Diamond diamond modality types. Okay, so the calculus, it's rather standard. So we have a functional fragment made of application and lambda abstraction, so as usual. And then we have the effectful fragment, which reminds somehow Moji's computational lambda calculus. So we have a constructor that takes a value and transforms it into a trivial computation. We have a sequencing that allow us to sequentially compose effectful computations. And then I also consider some operation symbols that act as sources of effects. So for instance, by taking binary operations, we can model non-deterministic and or probabilistic calculi, or by taking operations for reading and writing from stores, we obtain imperative calculi. And then, of course, I also assume to have other types, such as sum types or recursive types, so that we assume to have for recursion and other features. Okay, so the distinction that we have at the type level between, let's say, value and computation actually simply tell us that a computation may produce effects, but gives no information on the kind of effects that may be produced. So, for instance, take a calculus with primitives for output, right? Here we have two programs that compute the same value, namely 7. However, the program also performs an effect, namely it prints something during computation, whereas the other program does not. However, both these programs have type diamond int. So the type itself does not allow us to see the kind of effects that are performed by these two programs. And okay, Hod, I think there is a question.
Hi, yeah. Could you just go back to the previous slide?
Yes, sure. This one?
Yeah, where you've shown the squiggly arrow, there's an E on the right. What does that denote? Is that just the same term you started?
Oh no. I mean the squiggle arrow. I'm sorry, that's my fault. This is not something part of the symbolism. It's just like a conceptual connection. That the fact that we have a judgment that E is a program of type diamond A, give us the information that computation E, the program E, may produce.
Right. Sorry. Okay.
Produce an A values and possibly an effect.
Yeah, that was just my confusion.
No, my fault. I apologize for that. Okay, so I was saying, and the fact that the types do not give us enough information on the kind of effects that computation may produce has also some consequences on program equivalence. So for instance, let us consider a calculus, a probabilistic calculus with I/O primitives. Now, because as we have seen in the introduction, in a rather informal way, input-output is a non-commutative effect, which essentially means that the commutativity of sequencing does not hold. And therefore, even in the calculus with randomness and I/O, we cannot have, in general, soundness of commutativity of sequencing. So for instance, here we have programs in which we perform output, and of course, the order in which the output is performed, it's relevant, right? However, in this calculus, we may also have programs in which actually we do not perform any output operation or any input operation. So we just have, for instance, only randomness. And in that case, we might want to apply commutativity of sequencing. As we know, randomness is a kind of commutative effects, right? So we can apply that law. However, all computation or programs in this calculus have diamond types. So, and the type itself does not give us enough information to determine whether we can apply the commutative law or not. And there is, of course, a natural solution to this problem, namely to refine our diamond types by attaching to it notations that express the kind of effects that may be produced. So we may have a diamond types for computation that may perform commutative effects only, or for computation that may perform non-commutative effects only, or more generally for computation that may perform any kind of effects. And using this kind of refinement, Then we can also refine our program equivalence, and in that case in this case we are able to state that for computation with type diamond commutative, let's say, sequencing commutativity does hold, whereas we do not have it for computation of types diamond non-commutative, let's say. And this kind of approach is known with names. One of them is graded types, and there is a huge literature on these topics, started from types and effect systems at the beginning of the 90s. And nowadays there are also several works which focus on the semantics somehow of these kind of systems, especially using graded monads, which is the approach that we'll follow in this talk. And there is also a large body of literature on how these kind of type systems affect program equivalence, and in particular on program optimization. And I think that how the PhD thesis has also deals with this kind of topics. So how do we define graded types? Well, first of all, we need to fix what is called the effect algebra, which is just the algebra whose elements are the effects that can be produced. And this algebra must be a preorder monoid, whereas the monoid structure tell us that we have a trivial effect and that we have sequential composition of effects, whereas the preorder is not really necessary, but is something you might want to have for performing kind of subtyping somehow. And let me also remark that I also assume to have operation on this effect algebra that somehow reflects the operations that we have in the syntax of the calculus. So operation that acts as a effect producer somehow. Okay, let us see some examples. So we have already seen the effect algebra for commutativity, let's say. So we have elements that denotes whether we have commutative, non-commutative, or any kind of effects. The diagram shows the order. Okay, how do we have another question?
So thanks. This has really been very clear so far, which is wonderful. I'm just confused about one thing. You're distinguishing 4 points here, empty, C, NC, and top.
Yes.
Whereas I think for practical purposes, all we want to know is it's pure, it only has commutative effects, or it might have non-commutative effects, which is your T. But your NC, only non-commutative effects, isn't actually useful in practice. I just want to make sure I've got that right.
Yeah, you're absolutely right. You're absolutely right. Well, in this case, maybe you have just a chain with 3 elements, which pure, commutative, or any kind of effect would be better. Indeed.
Yeah, I think that would be good for this one. Yes. Okay, thanks. Very good so far. I'm really happy.
Okay, thank you very much. Okay, another example of an effect algebra is the one for graded divergence. In this case, we have just 3 elements, one for divergence, one for convergence, and one for no information, which means that the programs may converge or may diverge. We just do not know that. And another couple of examples. One is just a variation of the commutative, of the example of commutative effects, which give us graded reading and writing. So suppose we have some locations. Here we have elements that tell us that we actually have no imperative effects, or we read only from location, we write only to locations, or we may perform either reading and writing. And last example, which I think is kind of interesting because it show you how by choosing suitable effect algebra, you can model some interesting features, such as some forms of linearity. So for this example, forget about the order, just pick the monoid structure. I mean, if you add the order, it doesn't really work, but maybe there are some possible variations for that example. So here we have, we start with just 2 labels, O and C, for open the file and close the files, and we consider the monoid of words or list over these 2 labels. And for instance, using this effect algebra, we have the type diamond O, which means open the file once, essentially. Or we have the type diamond OC, so we have the list OC, which means that we open the file and then we close it, and we do that just once. Or we have the type diamond OO, which means that we have opened the file twice, which is something we might want to avoid. So this is just to stress that if we pick suitable effect algebra, we are also able to encode information not just on the kind of effects that have been produced, but also on the multiplicity or the order of effects. Okay, now we have an effect algebra. So what we have to do? Well, we just slightly modified our judgments. So we consider graded judgments, whereby we have computation, which has type diamond EA. So we have information on the effects produced. And typing judgments are modified in a kind of a natural way, taking advantages of the monad structure of the effect algebra, and also of the fact that we assume to have operation in the effect algebra corresponding to the operation in the calculus. All right, now we have the syntax. It's time to give operational semantics, which amounts to answer the question of what happens when we evaluate an effectful program. And to understand how to model the operational semantics, it is useful to have a look at concrete examples. So for instance, suppose we consider a non-deterministic lambda calculus, then we evaluate a program, and what we obtain is a set of values, namely the set of values the program may converge to. And that is modeled using the power set monad. And for a probabilistic calculus, what we have is that we evaluate a program and we obtain a distribution or a subdistribution of values, which is again modeled using the distribution monad. And the same patterns is present for other effects, such as global stores or exceptions. What we do, well, just do a light generalization and define operational semantics with respect to a monad. Actually, because we have graded types, what we need is a graded monad, which for us will just give you a very informal definition. A graded monad is just a family of mapping indexed over elements of the effect algebra that associate to any set A a new set TE of A, together with suitable maps, the unit and the multiplication of the monads, which are, of course, adapted to take into account effect annotations, right? So, for instance, the unit just works emphasizing that we are taking an array and we are producing a trivial computation, so one that produces the effect one. And whereas the multiplication just emphasizes the fact that we are sequentially composing effects. And as usual, having an equivalent way to define these constructors is using Kleisli extensions or monadic binding, which again should be adapted in the kind of natural way to effect annotation to the effect algebra. And now, fixed, so the graded monads define operational semantics using an evaluation function that simply maps closed computations to monadic values, right? And the evaluation map itself is defined in the natural way, so relying, for instance, on the unit and the binding of the monad. The only thing that should be clarified is how we define the execution of operations, right? Of the operation symbol we have in the calculus. And for that, we follow Plotkin and Power, and we interpret the operation symbols as algebraic operations on the monad, which again should be adapted to our graded setting, relying on the operations in the effect algebra. And for this talk, it's not necessary to know what is an algebraic operation. Just some computational intuition is enough. An algebraic operation is an operation whose behavior is independent of its continuations, which essentially means that operations commutes with sequencing in our calculus. All right, now we have all the ingredients. We can complete our definition of the evaluation map, and therefore now we have graded monadic operational semantics for our calculus. And now that we have a syntax and semantics, so to say, we need to understand what is program equivalence for our calculus. which amount to say when two programs are operationally equivalent. And of course, there are many answers, many possible answers to these questions. We may say the programs are equivalent if they are syntactically equal, or if once we evaluate them, we obtain the same results. And it's not hard to realize that both these proposals give too strict notions of equivalence. Or we may also take Morris-style contextual equivalence, whereby programs are equivalent if they are observationally the same when put in an arbitrary context, where of course one has to first fix a suitable notion of observation. And this, contrary to the previous one, is coarse enough, but it's rather impractical because it has a universal quantification over overall context. And another possible answer, which is the one that we will study in this talk, was given by Abramsky, and it is given by applicative bisimulation, whereby two programs are bisimilar or are equivalent if they are bisimilar as argument passing processes, which essentially means that what we have is a coinductively defined notion of function extensionality, the same function extensionality we have in mathematics, for instance. So a bit more precisely, let us say that a relation over programs, relation that respect types over programs is an applicative bisimulation if whenever it relates, if whenever it relates lambda abstraction, then it satisfies function extensionality. Whenever it relates other values that satisfy some natural clauses, so the values must have the same outermost constructors and related arguments somehow. And the critical point is to understand which clauses applicative simulation should satisfy when we relate computations, right? And good way to understand that is look at some concrete examples. So let us take non-deterministic calculus. Then applicative simulation tells us that if two computations are related, then we evaluate them, we obtain a set of values, and this set of values must be related using a suitable lifting of the relation. And the lifting is just the standard for all exist lifting that you have in a Milner style simulation. And you have the same pattern in probabilistic simulation. We start with two related programs, you evaluate them, you obtain distributions over values, and you require these two distributions to be related by a suitable lifting of the relation. And the lifting, it is written here, it is just the defining clause of Larsen and School probabilistic simulation. And the same pattern can be found in many other examples. So what is the moral? Well, the moral is, yes, how do we have another question?
So again, thanks. That's very clear. I just had 2 bits. You went by very quickly the slide before last. If you could just back up for a moment.
This one?
The one before that.
Okay.
Okay. Right. So both of these two are not symmetric. So you've got this relation diamond RA, but it's not a symmetric relation.
No, because here we are just looking at a simulation, which is the asymmetric relation. Then bisimulation can be defined starting from simulation by requiring symmetry. We will I will show you that in a few slides. But this is indeed asymmetric. This is just about simulation or program refinement, if you wish.
Okay, thanks. This is the first non-trivial talk I've seen in ages where I understood past the first half hour. So thank you very much.
Thank you. Okay, so the moral that we somehow extract from examples is that the notion of applicative simulation, and as we will see of bisimulation, is actually based on the way in which we lift relations from values to monadic values, right? So what we have to understand is what is a good mathematical notion of this way of lifting relations. And the answer was given 50 years ago by Barr using the notion, of a relator. So what is a relator? Okay, this is the scary definition. So a relator for a graded monad is just a family of of maps indexed by the elements of the effect algebra that takes a relation over A and B and lift it to a relation over TE of A and TE of B, right? So it's just a way from lift relation from, let's say, sets to monadic sets somehow. And we require this lifting to satisfy some structural properties, and some of them are actually quite natural. We have quasi-reflexivity, quasi-transitivity, monotonicity, plus some conditions on the monad structure, which require the unit and the multiplication of the monads to preserve relation, which can be expressed in a compact way using these lax commutative diagrams. So for instance, if we look at the one for the unit of the monad, this just states that if two elements A and B are related by R, then eta of A and eta of B must be related by the lifting of R according to the trivial effect one. And a similar reading for the multiplication of the monad. Right, so you may ask, okay, where this notion of relators come from? Well, there are many ways to understand where relators come from. A way that I find quite informative is by looking at the category of binary relation and relation preserving functions. So objects are just relations, and arrows are pair of functions that preserve relations somehow. And just a short remark, this is not important, so we could actually skip this one. Well, this category of binary relation is Cartesian closed. So with Cartesian product and exponential defined in the kind of natural way, so you can use this category also to study logical relations, at least for the simply typed fragment of the calculus. Okay, but that was just a remark. So if we look at this category and we look back at the conditions that we put on the notion of a relator for a unit and multiplication, well, what we see is that these conditions are just requiring eta and mu to actually be arrow in this category of relations, right? So what we might say is that greater relators give us suitable notions of greater monads on REL, on this category of relations. All right, now we have all the pieces, all the mathematical machinery to define applicative simulation. We have the same clauses as before, and now we require that if two computations are related, then we evaluate them, and the results must be related according to the relator. And because relators are monotone, they actually give rise to monotone operators on relations, so we can define applicative similarity coinductively as the largest applicative simulation, applicative bisimilarity as the largest symmetric applicative simulation. So now we have two notions, one for program equivalence, applicative bisimilarity, and one for program refinement, which is applicative similarity. And the main result is an extension of our results that Ugo Dalago, Paul Levy, and I proved 3 years ago, which simply states that under mild condition on monads and relator, which are very natural, applicative similarity and applicative bisimilarity are precongruence and congruence relation, respectively, which means that we can reason compositionally about equivalence and refinements of programs. All right, that was for effects, but I told you in the introduction that this talk is also about coeffects. So let us start to look at some of my ongoing research on coeffects. So in this part of the talk, I will just show you some kind of preliminary results. Okay, so far we have considered type system and equivalences which were concerned on what happens when we evaluate programs. But as we have in the introduction, it is also interesting to look at equivalences where we have also information on what kind of manipulation we can make on code, right? And that directly led us to the notion of a coeffect. And coeffect is a hot research topic. There's been a thread on types, on the mailing list types last week, which I think has stressed the fact that there are many people interested in coeffects, but also at the same time that coeffects are not really well understood yet, or at least that's my opinion on that. And just to give you an idea of the kind of the amount of research people are doing on coeffects in a recent year, here is a partial list of works on coeffects, and I have to apologize for omissions. I'm sure I omitted quite a lot of works. In particular, let me highlight two works, one by Marco Gaboardi and collaborators on the notational semantics of effectful and coeffectful calculi, and one by Dominic Orcad and collaborators on the language granule. And I mean, the kind of calculus and results and so on that I showed you, that I'm going to show you, were actually based on results and idea presented in these papers. Okay, so how do we add coeffects to our calculus? Well, first of all, we change the base of the calculus. So we start with the linear calculus, which means that code must be used linearly by default. Then we add graded necessity types or box types, which essentially are types whose inhabitants are values with capability, right? And the notion of a capability is mathematical abstraction describing the structural behavior of programs. So the kind of manipulation we have on those kind of programs, right? And before entering into the technicalities, let me remark that when we look at this kind of calculi, we are actually combining substructural and model type systems. And what I choose is to start with the linear type systems, and this is the kind of standard in the literature as far as I know. But there are other possible choices, such as relevant or even intuitionistic, starting with the relevant or an intuitionistic base, especially if one is interested in the modal aspects of the calculus. And it is still unclear to me whether linearity is the right way to go. As I said, these are ongoing research, so a lot of things are just at their very beginning. So there are things that I'm not sure about yet. Okay, so as I said, we start with the linear calculus, which means, for instance, that we are not able to type the usual combinator k, right? And what we do to overcome these problems, so to say, is to add graded box types. So, for instance, we can have a box type for affine usage of programs, or for relevant usage of program, or for intuitionistic usage of program. This way, for instance, possibly recovering the typing of K or other programs. But we may also consider modalities with kind of more qualitative flavors, such as the kind of modalities that we have seen in the introduction of this talk for security level, right? Whereby we can put information at the type level of whether a function is need to access a value with high security level or with low security level, right? And the kind of annotations that we have on these model types, as I said, expresses the kind of capabilities of programs, and more formally, they actually encodes the structural behavior of programs. And in order to model this notion of a capability, we consider a resource algebra. So as we have an effect algebra for effects, we have a resource algebra for coeffects, which is just a pre-order semi-ring. So this is the kind of standard structure that you find in the literature for modeling coeffects. Well, of course, variations are possible. There are people that maybe consider a continuous semi-ring or variations thereof, but more or less, this is the kind of structures you find. And let me show some examples of resource algebra. If we take just a one-element resource algebra, then we essentially recover a linear type system in the spirit of linear logic. If you take extended natural numbers, you recover type systems in the spirit of bounded linear logic. if you take non-negative extended reals, that you recover kind of notion of sensitivity you have in calculi for differential privacy, such as fuzz, or you can take any distributive lattice and you recover the kind of calculi for confidentiality of information flow that we have seen, for instance, in the introduction. All right, so now we have a resource algebra. Now we have types, we have modal types like box RA, which are types for values having capability R. But we also need to model programs that actually require arguments coming with capabilities. And for that, we perform a further refinement of our judgments, whereby now we consider judgments in which the environment can have linear variables, so placeholder for code that must be used linearly. And it may also have graded variables, which are just placeholder for code that comes with capability. So the code that can be manipulated according to the coeffect R. All right. Now we can finally define the calculus. This is, again, we have the linear fragment, which is pretty standard, just abstraction and application. Let me just notice that in the rule for application, because we have two pieces, so two environments which may have requirements on their code, we have to put those environments together and also to combine the kind of requirement. And this is done by extending the coeffectful sum, the resource sum, to environments pointwise. So that's the kind of natural way to go. And the effectful fragment, it remains pretty much the same for now. I will comment on that in a moment, but for now it remains pretty much the same. And the new part, let's say, of the calculus come from the structural fragment, where relying on the 0 and the 1 resource, we are able to perform weakening and dereliction, both on, let's say, value judgments and computation judgments. And then, of course, we have the coeffectful fragment, whereby we take a value and we can box it, producing a value with capability. And of course, in doing so, we also add new requirements of the environment. And if we have a value with capability and we have a computation that requires a value with capability, we can just somehow compose them, right? And that's the kind of elimination rule for the box modality. And as usual, we may assume to have other types, such as tensor type, recursive types, or even product types and other similar things. So let me now comment a bit on the calculus. So the first observation, Hode, we have a question.
Yeah, I was just wondering, with these rules, has the diamond become part of the judgment syntax, or why should I expect diamonds where there are?
No, these are the kind of observation I'm going to make. So the diamond at this point, and also, I mean, in general, diamond remains for computation types. So you cannot have diamond appearing in the environment, so for instance. So the environment can only have either linear variables or graded variables which are related to the box modality, not to the diamond modality. And the reason we have that is that this actually, I think that should be doable, provided that we modify a bit the calculus. I mean, having the diamond also as part of this graded judgment seems to me to not fit very well with the call by value fine-grained style of the calculus. Nonetheless, I agree that it would be useful to be able to have types, to have inhabitants for types such as a box diamond A, right? And at this moment, the calculus does not allow to have them, but what we can do is to introduce another form of sequencing which models interaction between effects and coeffects, right? Where we start with a computation E that produce a value, a linear value of type A, and we have another computation that requires a value with capability, right? And we want to sequentially compose the computation. And so the idea is that, say that our research as our usage, so what we need is to produce R copies of the value computed by E. So what we do in this case, well, intuitively, we just evaluate program computation E R times. We produce the R copies of the value, and then we just bind them to F and continue with the computation. However, you see that if we do so, then we also produce new effects, right? And that, of course, the kind of new effects that we produce depends on the effects we have. So if we have effects that just describe the kind of effects that can be produced, so kind of idempotent effects, that running the program twice, for instance, does not change the effect. However, if we have an effect algebra, which gives information on the multiplicity somehow of the effects, then running a program twice then changes the effects. So to capture this behavior, we just introduce suitable maps, which we may call monotone action, which are just monotone function that takes a resource, takes an effect, and produce a new effect, which intuitively is the effect that is the new effect that is produced if we run execute the effect R times in a very informal way, speaking in a very informal way. And this map is required to satisfy some structural properties which are very natural. I mean, these are just stating that, I mean, these are the kind of things that you would expect from algebra. Okay, and using these monotone actions, we can start to figure out what is this new sequencing rule. The last things that we need to understand is what happens to this environment here. Well, of course, if we run program E times, that we also need to have to multiply the resource somehow in gamma by R, right? And so we obtain, following this intuition, we obtain the final rules, in which we have the monotone action to produce new effects. We somehow scale the environment using the new resource, and we obtain this new typing. And let me just say that other options are possible, especially for what happens to the environment gamma. And if we look at a paper by Marco Gabardi and others, you will find a lot of other possibilities for this kind of typing rules. So that's the way in which we let effects and coeffects interact in this calculus. Okay, so that's the syntax and the typing for the calculus. This is something that may appear maybe not that natural, maybe just because working with call by value calculus is not the natural option. As I said, these are just preliminary investigations, so it may very well be possible that calculus should be changed to have something more natural. Okay, now that we have the calculus, we can define operational semantics essentially in the same way that we did before for the effectful calculus. And now it is important to observe that here in this operational semantics, coeffects do not appear, right? And that's something that, to the best of my knowledge, happens almost anywhere in the literature. So, for instance, if you take a calculus with differential privacy, then you do not see coeffects in the operational semantics. And therefore, we would like to understand, okay, how do we account for coeffects then? And possible intuition comes from the notational semantics, where one uses graded monads for effects and graded comonads for coeffects. But the problem here is that interesting comonads usually are not on set. So for instance, if we take as coeffects, the security level, just 2, low and high, then the semantics of the calculus, the denotational semantics, is given using sets indexed by security levels, whereby a type is interpreted as a type for values at low security level and types at high security level. And then you have indeed a comonad for the coeffects, which is kind of masking comonad. Or if you take as a resource the sensitivity, so you obtain a calculus for differential privacy, then the notational semantics of the calculus is given in the category of metric spaces. And the coeffects are interpreted as a comonad that just scale the distance. Right, so do we account for coeffects at operational level then? So the idea is that we indeed model coeffects using comonad, but this time on a suitable category of program relations. And what are these program relations? Well, these are, I call them resource relation. I'm sure they have quite a lot of names in the literature, and these are just relations indexed by element in the resource algebra. And I use this notation to state that V and W are values related by R given the resource R. Right. Okay, and again, another short remark. As standard relations form a category, we have a category of relations. Also for resource relation, we have a category whose arrows are just relation preserving functions, or pairs of resource preserving functions. And again, as before, just as a remark, this category is actually a monoidal closed category, and that's because the resource algebra has quite a lot of structure, so it allows us to model tensor product and exponentials. And if you're familiar with this definition, you immediately recognize that this structure actually captures the way in which we account for resources. So we need maybe to be able to split resources or to add resources and so on and so forth. And of course, there are also other constructions in this category like Cartesian product. And that is just a remark to say that this category can be used as a base for studying logical relations for coeffectful calculi. All right, end of the remark. Now let us look at applicative simulation. Well, this is now a resource relation which behaves as expected using extensionality at the level when it deals with lambda abstraction. On other value types, it behaves in the natural way, just mimicking the constructions that we have in the category of resource relation. What we have to understand is what are the clauses for boxed values and computations. Well, for computation, actually things are kind of easy. We just take relators, create the relators as before, but this time on the category of resource relation. So nothing changed essentially. That's pretty much the same. The interesting construction is the one for modeling boxed values. And in that case, we may consider something like graded comonadic relators or correlators. I don't know whether these kind of have a name, which are just map that take resource relation over, let's say, with domain and codomain A and B, and map that to a new resource relation with the same domain and codomain. So the domain and codomain remains the same. That's because coeffects are not visible somehow in the operational semantics. What changes is the resource relation, so the way in which we deal with resources, right? And this lifting is required to satisfy these structural conditions, which essentially means that what we obtain is kind of a graded exponential comonad on this category of resource relations, right? Last piece of the construction that we need is how these relators and correlators should interact. And for that, we have we should consider interactive law. Here we have one possibility. I do not want to enter details. Just let me remark that all these interactive laws are just way to swapping box and diamond modalities, essentially. All right, and now we are done. Now we have all the clauses for defined applicative simulation. On computation, we have relation lifting. On values, we have just standard clauses. And on boxed values, we have correlators somehow. Applicative similarity and bisimilarity can be defined as usual coinductively. And now the main results, well, I do not have main result. As I said, this is ongoing research. I just have a conjecture that this way what we obtain are congruence and precongruence relations. And I'm working out proofs in these days. Okay, so that's all. Let me conclude. So what we have seen are coinductive techniques for graded effectful languages and some ongoing work on equivalences for graded effectful and coeffectful languages. Somehow I've worked out the math, which I think also support investigation on logical relations on these kind of languages. But as I said, this is an ongoing research, so there are still a lot of things that to be explored. In particular, what I think is kind of interesting is to understand better what are resource-sensitive equivalences for programs. And that might mean to look at logical relations or open equivalences or even environmental equivalences. And we have some work in progress with Ugo Dallago on environmental equivalences for linear calculi, but this is just, I mean, the kind of the topic of resource-sensitive program equivalence is something that I think is largely unexplored, at least for these kind of languages. Okay, thank you very much. Sorry if in the end I went a bit fast. They took me more time than expected. So if you have questions or remarks or observations. Okay, Odd, we have 4 or 5 questions, I think.
If you have a question, please raise your hand. See a question from Jesse. Jesse, don't forget to unmute yourself. Jesse, we still can't hear you.
You're still too quiet, Ohad.
Okay. Jesse, please unmute yourself.
Hi, thanks for the talk. It was great. When you mentioned the mismatch between fine-grained call by value and what you were looking for, do you know if call by push value would be a good solution?
Maybe. I do not know. I'm not that expert on this kind of computational calculi. It may be. I mean, as far as I know, call by push value as a natural support for doing the tank of computations, and that maybe could be a way to improve these calculus for effects and coeffects. But this is still something that I should understand in a much better way.
Okay, thanks. Phil?
Hi, so thank you again for a very nice talk. I really like that. I have a bit of a stupid question about the relationship between effects and coeffects. So effects are modeled by a monad, coeffects are modeled by a comonad. Any monad you can get as the product of an adjunction with either the Kleisli category or the Eilenberg-Moore category. And if you swapped those two functors, you'd get a comonad. So does that mean we could always treat any monad as a comonad and any comonad as a monad? I think that doesn't work, but I'm not sure why. Maybe one concrete version of my question is we've got a comonad for dealing with linear logic. If you swap that about and got the monad, what monad is that? I'm trying to work it out, but I can't. I'm just wondering why this well-known thing doesn't give us a road in here. It seems to me like it doesn't. I'm not quite sure why.
That's a tough question. And honestly, I do not have an answer. Not at all. Not even a bet, actually. I would say, or a guess. So I'm really not able to answer your question. I'm sorry about that.
Okay, well, maybe it wasn't a stupid question then, but thanks again for the talk. I enjoyed it.
Thanks to you. Thank you.
Thanks, Phil. Gordon?
Yeah, hi. Also, thanks for a very nice talk. Hey, so I don't know much about Coeffects, so this is a naive question, like following in Phil's tradition. So in the case of monads, free algebras form a very large class of monads, which give almost all the examples, except for things like continuations. So how about the comonads? Is there some natural class of comonads, or do you, which give you all the effects, all the resources that you normally come across?
That's also an interesting question, and yeah, I do not have an answer for that. I mean, there are, of course, I mean, people have looked into co-free comonads. I don't know whether there are nice examples of that for modeling Coeffects. I really have no idea.
Right, no, it's more the other way around. You take a list. You gave lists of Coeffects early in your talk. So can you get all of these examples by some simple kind of comonad? That's the kind of question.
No, I don't know. I should think about it.
Yeah. Okay. Well, thanks very much.
James?
Me? I guess I'm talking now. So you talked early on about having multiple different effects in a program, and I think I kind of lost where that went during the talk, because we seem to require kind of one monoid for the effects and one semi-ring for the coeffects. Do you have anything to say on combining effects and coeffects, or combining effects and then combining coeffects?
So did you mean if we have kind of operations starting, let's say, from two effect algebras to combine them together for performing a new effect algebra, or
Yes, something like that, yeah. So you're both doing non-determinism and, I don't know, I/O or whatever.
Yes, there are operations for combining effect algebras on one hand and the resource algebra on the other hand. The only one, such as products, for instance, the only one that now comes to my mind, which I think it's very nice, is one given by Dominic Orcad and collaborators in a paper at ICFP last year, which is the interval resource algebra. So you start with the resource algebra, and we build a new resource algebra, which is just made of intervals of elements of the original resource algebra. And in that way, they can model things like linear types, affine types, relevant types, but also kind of intermediate types, such as restrictive affine types or permissive affine types and that kind of things. But honestly, besides that, there are, at this moment, I'm not able to remember any other interesting construction.
Yeah, so I mean, just being able to combine them, say with, I don't know, like direct product or something, seems an interesting thing to consider.
Well,
yeah, I'm familiar with the Orchard paper, and I still think of the ways that they combine some of the coeffects as ad hoc. But if you've seen, if these intervals have something less ad hoc to them that you've seen and I haven't, then that'd be interesting to.
Yeah, I mean, the example with the interval resource algebra, I think it's pretty interesting. Other, as I said, other let's say enlightening operations for combining effects or resources. I'm not really aware of other kind of super nice operations for these kind of combinations. But as I said, I mean, coeffects are, I think, are largely not understood yet. So I agree that even understanding whether have good ways for combining this algebra, it's something interesting to be done. And by the way, it may also be possible that the way in which people are studying coeffects is not even the right one. I mean, as I said, we are just exploring things, and well, researchers in general are exploring these topics, and a lot of things are not well understood yet.
If I could maybe add a secondary question as well. I was wondering whether the presence of these unboxed variables in the context had anything to do with being able to combine coeffects, or generally why you took that decision to include such things.
You mean the fact that in environment we have graded assumptions, we can have graded variables?
And also ungraded ones.
Well, the fact that we still have a distinction between, let's say, graded and non-graded variables comes from the fact that we want to be able to have a kind of substitution lemma, right, in the calculus, and this is kind of tricky, to the best of my knowledge, when you deal with this kind of model calculi. So the distinction comes from regional work on dual sequence calculi, or those kind of things, in which you have a distinctions in your environment, let's say, between the intuitionistic part or the linear part or other things, and that simplifies the way in which you can perform substitution. That's one point. The fact that I have graded assumptions, I mean, is used because you may want to have to write down computations which have some requests on the kind of access or manipulations that they want to perform on variables, right? And having this kind of graded variables on one hand and model types on the other ones allows you to perform kind of compositions, right? Or which is modeled using the cobind of the monad, for instance.
Yeah. So what I'd say is, with respect to substitution, you might want to see my very recently submitted extended abstract that shows that you can do it perfectly well with graded variables. I can send you it if you want.
Yeah, if you can send me a link or whatever, that would be great.
Okay.
Thank you very much.
Okay, let's go Sam and then Golden.
Okay, that was me first, wasn't it?
Correct.
Yeah. Okay. So are you familiar with the work by Alex Simpson and Niels Fornevelt on behavioral equivalence for, the title of the paper is Behavioral Equivalence via Modalities for Algebraic Effects?
Yes, I'm familiar with their work.
Right. How does that relate to your work here?
Sorry,
well,
Christina Matasha's follow-up work on that as well, if you're going to compare.
Okay, so so the connection with my work that I'm aware of is about the first part of this talk. So the equivalences for effects, right? To the best of my knowledge, their work on logic does not deal with the coeffects. And the connection is as follows. So they define a logic for studying programming languages with algebraic effects, and their logic induces a preorder and then an equivalence, which they prove to be a congruence using the kind of techniques that they have. So by showing that they actually have a relator, right, induced by the logic, and because the relator satisfies the defining condition of our relator, which means, for instance, that it behaves well with sequencing, and with other constructors, they can prove that what they obtain is a congruence. So the result that I have, that we have together with Ugo and Paul, are holds for any relator. So in particular, they should hold for the relator induced by their logic. The other way around, namely whether any good relator can be characterized using logic, a modal logic like the one that they have, I think it's something not known. At least I do not know any results in that direction.
Okay, thank you.
You're welcome.
Gordon, go ahead, please.
Yeah. Okay. So two questions. One's a small technical question. When you're defining relators, I think you had a condition on converses. Is that right? I saw some little circle.
Yes, you're right. Absolutely.
But how does that come up? Is that because you want to do something about equivalence relations later on? Is that the point?
That condition is essentially to ensure that you can that you have the kind of functoriality conditions you need. So that condition is usually expressed using requiring things like that if you apply the relator to the inverse image of the product of two functions, we obtain I got a bit confused. So that conditions is usually expressed requiring that the relator of the kernels of two functions or something like that is included into the kernel of the monadic lifting of the function itself, or something like that, which essentially means that you can you preserve commutative diagrams somehow. But you can recover that conditions using the one about converses, because converses can come up when you want to do calculations like composing functions and relations. And the way I use that condition is just because it is shorter to be written down.
Okay, so that, okay,
thanks.
It gives me. Sorry, go ahead. Sorry.
But if you look, for instance, at papers, or even there's this book on monoidal topology, they use relators quite a lot, especially relators, let's say, over kind of relations over quantals, and they use these kind of conditions using the converse. And but that's exactly what they need to express this kind of preservation of kernels. Sorry if it was a bit sketchy.
No, it gives me some feeling for a little bit of feeling for what's going on. I'd quite like to know what the book on monoidal topology is. Maybe you could send it. Details to me. Thanks. So my second question was, supposing your conjecture is true, hopefully it is. So then you'll get that your kind of applicative bisimulation implies the contextual equivalence, I guess, where observational equality is given by some relator. So then the obvious next question, just to jump ahead, would be if you have any idea about the converse.
I suspect the converse does not hold, and the reason comes back to actually can be found in one of the two motivating examples that I show you at the very beginning of the presentation, the one by Deng and Zhang.
That guy, yeah. No, I remember it. Okay.
Yeah. Okay. And the point with that example is that you really need to shift from bisimulation to trace equivalence, because on one hand, I mean, if you add resources, you may be able to deal with if you shift to resource relation, whatever they are, you may be able to deal with resource sensitive aspects of the calculus. But there you also have a problem with branching, right? And bisimulation is by its very nature sensitive to branching. And if you look at the conclusion and future work, I shortly mentioned that we have this environmental equivalence here at the bottom slide, and that equivalence actually it's fully abstract for a calculus with linear types, the bank modality, and algebraic effects. And the way we obtain that equivalence is by working with environments in which you have intuitionistic terms and linear terms, and by lifting the equivalence. So we do not play with programs themselves, but with monadic programs. And in that way, Bisimulation somehow becomes trace equivalence. But the price to pay is that the equivalence is very hard to use, and the meta theory is a bit of a mess. I mean, proving the congruence, it's a bit of a disaster.
Oh, okay, so maybe you could send me that paper. Or I can look in your site to find the paper, I guess. Yeah. Okay,
yes,
thank you very much.
You're
Sorry.
welcome.
Yeah.
Okay, so thanks a lot, and let's thank Francesco again for a very long talk and a very long discussion afterwards. So thanks again for joining us, Francesco.
Thanks to you, and apologize if I was not able to answer all your questions, but thank you very much.